Welcome to this review for Unit 5. So far you've learned a whole bunch of jargon about different ways that we apply physics and motion and velocity and acceleration and mass and how this all works together. The purpose of this chapter is to give you several real-world examples of how these physical laws happen in your everyday life. So, the last time you went in an elevator, you probably weren't thinking that you represented a huge array of physical science principles, but you actually did. So we're going to go over that here today. Here we are moving from, let's say, the third floor down to the bottom floor. You're initially at rest when you're inside of your elevator. This is going to be you. Put yourself here in your elevator. What is your velocity? Well, let's analyze this. Are you moving yet? No, you are not. You have a velocity of 0. Now, for the purposes of this demonstration, we're not going to be talking about specific values of velocity and acceleration, because we'll leave that for the physicists and the mathematicians. We're just going to be using arrows to help represent that. Your acceleration. Do you have an unbalanced force acting on you? No. We've learned over the last couple chapters that when you are in a state of constant motion or not moving at all, gravity is acting on you, the Earth is pushing back up on you, and those forces completely cancel each other out. So your acceleration is 0. Now let's think. In the next frame, you have just begun to accelerate downward. So your velocity has changed. We've learned from earlier videos that when your velocity changes, that is called an acceleration. So your velocity has gone down. It has increased downward. Your acceleration had to be the thing that caused that. So you accelerated downward. While you're in constant motion, you are in a constant reference frame, a constant inertial reference frame. Your velocity is going to be constant in the downward direction. Are you accelerating? Let's analyze the forces. Hopefully this will be a model or a template for you for all future problems you could be faced with. If you have unbalanced forces, you are accelerating. If you do not have unbalanced forces, you are not accelerating. So, are we accelerating? We are in constant motion. No, gravity and the force from the Earth upward are balanced. What about when we are decelerating? You're moving in a downward direction, but it's not going to be as strong as it was here or here. You're beginning to slow down. Now, did an acceleration cause that? There had to be an unbalanced force that caused that. So you were actually accelerating upward. Now, for many of you, this may go against the grain. How can you accelerate upward if you're moving down? All that means is you are moving down less fast. So you are decelerating. Think about this in the context of a car. If you are moving forward in a car and you slow down, you are accelerating backwards so that you slow down. Let's go through several more examples. Our next example is going to be a fly and a train. Now, hopefully you talked about this in your lectures. Here is my beautiful, beautiful train. Kind of looks like a semi-truck. Bear with me. And you have a fly. When comparing the masses of these two objects, we can represent it graphically using Newton's second law. We have a mass of the fly compared to the mass of the train. So this is going to be our train. This is going to be our fly. Now, when the fly hits the train, we've all seen what happens when a little bug hits your windshield. It's going to be instantly squished, basically vaporized. It will cease to exist as a bug. But let's analyze it from a perspective of forces with the equation force equals mass times acceleration. We've already seen that the fly has a small mass, the train has a very, very large mass. So one of these is going to have to accelerate more than the other one will. This mass needs to be multiplied by a really big number to get us to the size of this force. And this mass needs to be multiplied by a very small, teeny-weeny number to get us to be this force. So the acceleration that the train undergoes is going to be very, very small. And the acceleration that the fly undergoes is going to be enormous. Using Newton's second and third laws, we can now understand what happens when a little fly, splat, goes into your windshield or the windshield of a train. The train has a huge mass, accelerates barely at all. The fly has a tiny mass and accelerates greatly, so much so that it completely squishes. Let's go through another example. Now that we understand what happens with a fly in a train, we can have a concept of what air resistance is. Air resistance, or air molecules, are tiny little flies that are pelting against your body all the time. If you've ever tried walking really, really fast into the wind, you know exactly what I'm talking about. Think about when you go swimming. Those molecules are much bigger and stop you from moving forward a lot more than air does. Air, just like water, is also very fluidic, but it acts more like the fly, where you hit those little particles and they slow you down just a little bit. But because there's billions and billions of air molecules, they don't stop you completely. So right here we have our airplane. We have a skydiver that has just jumped out of the airplane. This skydiver is going to continue to accelerate because there is a force acting on them. It is not balanced. It is an unbalanced force. The force is gravity. Now, right as this skydiver jumped out, they also started to experience air friction, air resistance, pushing up. But as you can see, the force of gravity is larger. It is an unbalanced force that will cause an acceleration downward. Now, eventually the skydiver will come to a point where it has reached what is called terminal velocity. Terminal velocity, depending on your altitude, is somewhere between 100 and 150 miles per hour. At that point, the force of gravity and the force from air resistance are equal to each other. G for gravity, air resistance. At this point, the skydiver ceases to accelerate and continues at that velocity until they either hit the ground or hopefully deploy their chute. Here's their beautiful chute. Now, as soon as this chute gets deployed, which of these values changes? They now have more surface area for the air to push on, so it has to be their air resistance. Their air resistance increases, the force of gravity stays the same. So what happens? Our skydiver slows down. He accelerates upward even though he is moving downward. His velocity is downward, he accelerates upward and slows down to the point where the skydiver is able to drift, glide slowly towards the ground and land safely. Let's do a final example. Let's talk about orbits. Orbits are extremely important for discussing what happens out in space, as well as how to get up out into space. This is a representation of the Earth. Let's put a cannonball right here, a cannon. If we shoot a cannonball out of here, it will have a certain amount of velocity, a certain amount of mass, acceleration. We don't care about those values. We just know that eventually it's going to hit the Earth because of gravity. If I launch that cannonball even faster, it's going to hit farther and farther and farther until there comes a point where it never hits the ground, where its speed is enough to where that cannonball is going to be carried all the way around the Earth and to the other side. That's exactly what is happening with orbiting shuttles, orbiting satellites, even the Earth going around the sun. We are constantly being pulled towards the center of the Earth from gravity. But because of Newton's first law, the law of inertia, we never hit it. We continue trying to move forward while gravity pulls that cannonball towards the center of the Earth. Thank you.